Hello everybody. In today's video, we will be talking about the electric field. Now in the last video, we talked about electric force and Coulomb's law, and the electric field is actually very related. So let's jump right into it. First, we know that the force acting on the electric force, the formula for it would be equal to K Q1 Q2 over R squared. Now let's say that Q2 is a test charge. The test charge to get the electric field. At distance R from Q1. So since it's a test charge, when we remove it, we also remove it from the equation. However, it won't become electric force anymore. The electric field given by the symbol E is equal to actually K Q1 over R squared. Since Q2 is a test charge, we could say that E is equal to F electric over Q test, meaning the test charge. Now, an example of this would be, for example, if you have a positive charge here, let's just call it positive Q, and a test charge here, let's call that Q null. What is the, and it's also, let's say 1 meter apart. What is the, let me just place this in a better spot. This is Q null, and this is a test charge. What is the electric field passing through the point of the test charge? Now, we can do either the KQ1 over R squared or F electric over Q test. I'll do both methods first. Now we have here F is equal to KQ Q null over 1 squared, which is just equal to KQ Q null. Now the electric field passing through that charge is equal to F electric over Q null. That's equal to KQ Q null over Q null. That's basically equal to KQ. Take note na that K is equal to 8.988 times 10 raised to 9 Newton meter squared per Coulomb squared. The unit of electric field is actually newtons per coulomb. So this is newtons per coulomb. Now let's use the formula that does not go through the electric force. That would be equal to KQ over 1 squared, which is basically just equal to KQ newtons per coulomb. And that's our final answer. Let's take an example. So if you guys remember the given from the last video, we have 4 charges with equal magnitude that are positioned on a square with side length 0.75 meters. We'll be using the same given here. However, we now have a value for Q, which is equal to 5 nanocoulombs. we are also given that there's a negative charge in the upper right hand corner, and the rest are positive charges. Right now, we are asked to find the magnitude and direction of the electric field in the center of the square. So we're getting the electric field at this point. Oh, and by the way, I forgot to tell you guys this, but the electric field, if you can notice, for example, let's say that a positive charge is red and a negative charge is blue. There are what we call the field lines. It can also be seen when you place some iron filings on a magnet. You would actually be able to trace out the field lines using the iron filings and the magnet. So it's the same thing. There are 3 rules to field line creation. The first rule is that positive charges field lines move away from the charge. A negative charges field lines move toward the charge. The second rule is that field lines never intersect. And the third rule is that the more field lines are in an area, the stronger the electric field is. The stronger the electric field. So we could say that the field lines going through this is away from the charge. And the field lines in this are moving toward the charge. But how about if we want them to be closer together? What would the interaction between the field lines would be? Let's use this diagram here in the top. So away from the charge in the positive and towards the charge in the negative. So it becomes like this. And here, same thing. However, it will arc, kind of like that. Same thing here, it will arc down. And also like this. Over here, it would just arc like that. Here, it will arc like this. And since these ones are moving on opposite sides, it goes like that. And finally, we have this direction here and this direction here. So this is like the interaction between a positive charge and a negative charge. Now, if you have a charge with like signs, 2 charges with like signs, let's say for example, this is Q and this is also Q. No matter what the charge, I'm using it in white because it's just basically like this, but with the directions reversed. I forgot this one. So it kind of looks like a spider, like that. This is with 2 like charges. This is with 2 opposite charges. Now moving back to our problem over here. Let me just copy this real quick. copy. Okay, there we go. Now, moving back to the question that we have. There. What is the magnitude and direction of the electric field at the center of the square? Now we know, let's draw the field lines first. Okay, I'll just erase this E. Let's draw the field lines first. So this field line would move towards that, move towards the charge. This field line will move away from the charge towards that. This field line would move like this, and this field line will move like that. Now, as you can see, it's kind of symmetric. 5 nanocoulombs here, 5 nanocoulombs here. So these field lines can actually already be cancelled. So what is actually being talked about in the problem is just find the total field line, total electric field in this diagonal. So here, let's call this Q1 and let's call this Q2. Now, the electric field is just basically E1 plus E2. Now, to get E1, I forgot the arrowhead. To get E1, that is equal to K times 5 nanocoulombs. So it's 5 times 10 raised to negative 9 over R squared. Now, what's R? Now, we know that since this is 0.75, this is 0.75, this would be 0.75 square root of 2. Now, we want half of that. So this becomes 0.75 square root of 2 over 2. This is squared. E2 is the same concept. That would be equal to K times, this is only just the magnitude for now because we know the direction already. K times 5 times 10 raised to negative 9 coulombs all over same distance. It's 0.75 square root of 2 all over 2 squared. Now, to get E total, we just simply add them, or basically we multiply them by 2. This is K times 5 times 10 raised to negative 9. If we square this becomes 0.75 squared times 2 over 4. And that's equal to, this then becomes 2. This becomes 2K times 5 times 10 raised to negative 9 all over 0.75 squared and multiplied by 2. So the electric field then becomes, the total electric field then becomes 4 times K times 5 times 10 raised to negative 9 all over 0.75 squared, and computing that through our calculators, we would get the value of 319.57 newtons per coulomb, and that is our final answer. Now guys, if you like this video, please like and subscribe to my channel. I would greatly appreciate it, and it will help the channel a lot. And if you have any questions, just leave them down in the comment section below. And also comment down what topic in physics and chemistry and computer science would you like me to cover in my future videos. That is all for now. Thank you and goodbye.